Your CPU is running billions of instructions every second. It's deep in a calculation, completely absorbed when you press a key. And somehow, before your finger even lifts, that keypress has reached the kernel, been turned into a character, and shown up on your screen. How? The CPU wasn't watching your keyboard. It wasn't polling your network card. It wasn't babysitting the clock. It was interrupted. Every keypress, every network packet, every disk read, every timer tick, tens of thousands of times per second, yanks the CPU away from what it was doing. And somehow, nothing breaks. This is how interrupts work. Before we talk about interrupts, let's talk about the alternative. Imagine if the CPU had to check every device itself, a loop that asks, every few microseconds, keyboard anything, network card anything, disk anything. That's called polling, and it's a disaster. Most of the time, every device says no. So the CPU burns almost all of its cycles asking questions with no answers. Now flip the model. Let the CPU do real work, and let the device raise its hand when something happens. That's an interrupt. The device pokes the CPU on the shoulder, the CPU drops what it's doing, handles the event, and goes right back to work. Zero wasted cycles, instant response. So how does a device physically poke the CPU? Each device has a wire, called an interrupt request line, or IRQ, that runs to a small chip called the interrupt controller. On modern machines, that's the APIC. The keyboard sits on IRQ1, the timer on IRQ0. A network card might be on IRQ11, a disk on IRQ14. When the device has something to say, it raises voltage on its line. The APIC is a kind of receptionist. It sees the raised line, figures out which device it came from, assigns it a priority, and then pulses a single wire going to the CPU, called the INT line. That's the signal that says, stop, look at me, something needs attention. The CPU has been poked, but it doesn't know what to do yet. The APIC hands it a number, an interrupt vector, between 0 and 255. That number is the only clue the CPU gets. So the CPU looks the number up in a table. This table is called the Interrupt Descriptor Table, or IDT. It has exactly 256 slots. Each slot contains a pointer to a function, the handler that should run for that vector. Vector 0 points to the divide by 0 handler. Vector 14 points to the page fault handler. Vector 33 points to the keyboard handler. The kernel sets this table up when it boots. From then on, the IDT is the switchboard. It turns a number into a piece of code. Let's follow an interrupt all the way through. Step 1, you press a key. The keyboard controller raises its IRQ line. Step 2, the APIC receives the signal and sends vector 0x1 to the CPU. Step 3, the CPU finishes its current instruction, then pushes its program counter, its flags register, and its stack pointer onto the kernel stack. Step 4, it reads slot 0x1 of the IDT, finds the address of the keyboard interrupt service routine, and jumps to it. Step 5, the handler reads the scan code from the keyboard, adds it to a buffer, and tells the APIC, I'm done, an end of interrupt signal. Step 6, the CPU executes IRET. It restores the saved registers and jumps right back to where the program left off. All of that in a few microseconds. Let's zoom in on that moment of interruption. Your program is running in user mode, what the CPU calls ring 3. It has limited privileges. It can't touch hardware directly. When the interrupt fires, the CPU does something surgical. It automatically saves the program counter, the flags register, and the stack pointer, then switches from ring 3 into ring 0, kernel mode. Now the handler can talk to hardware. It can read device registers, touch kernel memory, ACK the interrupt controller. When it's done one instruction, IRET pops everything back off the stack. Flags restored. Program counter restored. Privilege level dropped back to ring 3. And the program resumes on the exact instruction it was about to execute. It never even knew it was paused. There's a problem with running code inside an interrupt handler. While the handler runs, other interrupts get delayed. If the handler is slow, the whole system stutters, missed packets, dropped keystrokes, laggy audio. So real operating systems split the work in two. The top half is the interrupt handler itself. It has one job: be fast. Acknowledge the device, grab any urgent data into a buffer, and get out, measured in microseconds. The bottom half runs the real work later, with interrupts re-enabled. On Linux, that's a softerk, a tasklet, or a work queue. Think of it like a paramedic and a hospital. The paramedic stabilizes you in 60 seconds on the scene. The real treatment happens in the hospital. Same pattern, same reason. So far we've been talking about hardware interrupts, but there are actually three kinds. First, hardware interrupts. An external device raises an IRQ. Keyboard, network card, disk, timer. Asynchronous, they happen whenever. Second, software interrupts. Your program deliberately triggers one, usually to ask the kernel for help. Every system call, read, write, open, is a software interrupt. The program executes a syscall or int instruction and jumps into the kernel on purpose. Third, exceptions. These come from the CPU itself when something goes wrong. Divide by 0. Access a bad memory address. Hit an invalid instruction. Three very different triggers, but they all route through the same place, the IDT. Same table, same mechanism. The CPU doesn't really care where the interrupt came from. The real world is messier than a clean diagram. A single IRQ line is often shared by multiple devices. When it fires, the kernel walks a linked list of handlers and each one checks, was it me? The first to say yes handles it. Interrupts can also be masked. If the kernel is in the middle of updating a shared data structure, it can run cli, an instruction that tells the CPU, ignore interrupts until I say otherwise. That's how it protects critical sections, but masking is dangerous. If you forget to re-enable or you mask for too long, the whole system freezes. And interrupts can be nested. A higher priority interrupt can preempt a lower priority one mid-handler. This is why writing good interrupt code is considered some of the hardest work in systems programming. So here's the picture. Every keypress, every network packet, every disk read, every timer tick. All of them are a device raising a wire, an APIC multiplexing those wires, a CPU jumping into a handler through a table, a few registers pushed and popped, and a program that never notices it was paused. This is the mechanism that makes your machine feel alive, responsive to the world while doing a million other things. It's one of the most elegant collaborations between hardware and software ever designed. Thanks for watching. If you like this, stick around. There's a lot more of how your computer actually works where this came from.